Okay, guys, what did we do in class? Well, we learned how to reflect points across an axis, like reflecting this point xy across the x-axis. We were able to develop an algebraic way of describing that. To take a point xy across the x-axis, we leave the x-coordinate alone and we negate the y. We also learned how to flip a point across the y-axis and get a similar algebraic formula. The third thing we did was learn how to reflect points across arbitrary lines, like this line I have at x equals 3. But I didn't give you a formula for that, and that bothered one of my students a lot. My student Anna intuitively knew there had to be a formula for it, but she's in 9th grade in Math 2 and maybe didn't have the algebra techniques to communicate what she was thinking to me. Here's what I think she was thinking. We're going to find out. It's a pretty simple formula. Let's look at what we did in class. We would take a point, like this point at 5, 2, reflect it across this line x equals 3, and you would tell me the new coordinate. And how did you do that? You might have just intuitively seen that if the x-coordinate is at 5, and this line is at x equals 3, that distance there has to be 2. Well, intuition isn't going to help us develop a formula, so I'm going to make us do a little math to figure out what that distance is. What we can do, again, we're not worried about the y-coordinate, we're only looking at the x. I can take this 5, and then I can subtract 3. 5 is the x-coordinate of the point, 3 is the value of the line at x equals 3. If I subtract 5 minus 3, I get 2. So that tells me this distance is 2. Therefore, I need this distance to be 2. If this is at x equals 3, then this coordinate has to be 2 units to the left, which is at the point 1, 2. So I calculated a distance, 5 minus 3, and I used that to find the coordinate of this point. Okay, let's see if that works up here. I have the point 2, 4. I want to reflect it across the line x equals 3. What did we say we needed to do? We need to take the x-coordinate of the point and subtract the 3, because the line is at 3. Does that give us the distance from that point to the line? It doesn't exactly. 2 minus 3 is actually negative 1, and since we're dealing with distances, we don't want negative distances. So in fact, to calculate these distances, I need absolute values around this. It's not just 2 minus 3, it's the absolute value of 2 minus 3. I can't have a negative. It's not 5 minus 3, it's the absolute value of 5 minus 3. So that's how I didn't finish this. This distance, 2 minus 3, is negative 1. Absolute value is 1. So that distance is 1. That means this distance is 1. And that means that point has to be at the point 4, 4. Computing with the x-coordinate, and I know the y-coordinate has to be the same. So what I want to do is this problem again, but instead of giving you specific points and a specific line, I'm going to use variables for the point coordinates and the value of the line. We need to use letters so that we have a formula at the end. Let me erase the board and we will get started. There, I have a new setup. I have drawn in a very similar picture, but now I'm telling you the line is at x equals a, not 3, just some number a. I'm telling you this point is xy, and it's going to map to a point x prime, y prime. That's the notation we used in class. Okay, from the problem we just did, what do we know? We know that this distance from the yellow point to the reflection line is the x-coordinate minus the value of the line, x minus a, in absolute value bars. That's this distance right here. We calculated that a moment ago. We know that distance has to be the same as this distance here. But what is this distance? This distance is the coordinate, the x-coordinate of the point minus the reflection line is the same thing. In this case, x prime minus a in absolute value bars. That's that distance. So I have a way of computing the two distances that I'm concerned with and I know that they have to be equal. Notice I'm not dealing with y's because I know the y coordinates are still going to be the same. So let's use these two absolute value expressions to come up with a formula. I know that x prime minus a has to be the same as x minus a when I put them both in absolute value bars. Now, does that mean that I can just remove the absolute value bars? Well, not necessarily. If I tell you that the absolute value of something is 2, that something can have two different values. It can be 2, it can have the same sign as 2, or it can be negative 2. It can have the opposite sign of 2. So when I'm solving this absolute value equation, I need to take two cases into account. One where the two things inside agree, x prime minus a equals x minus a. And I also need to take into account when they have opposite signs, because the absolute value strips those signs away. I need to say x prime minus a is equal to the opposite of x minus a. And I'm going to solve these two equations to see if I can get a formula for the x coordinate of this transformation. That's what Anna's formula wants to be. All right, so to solve this, I want to solve for x prime. I want a formula that gives me the new coordinate. So I'm going to add a to both sides here. The a's will cancel on that side. I get x prime equals, the a's cancel on that side too. It says x prime and x are the same value. In math, we call that a degenerate case. It's saying that the reflection goes right back onto itself. That's not helpful. That's not the formula we want. Let's solve this formula for x prime. I notice I have parentheses here, so I need to distribute this negative in. If I distribute that negative in, I'm going to have a negative x plus a. Look carefully. Negative x plus a. And I'm going to write that like this. I still have a negative x plus a. I just wrote it in the reverse order. And that's equal to x prime minus a. Great. Let's solve this equation for x prime. You can add a to both sides. This time, when those cancel, I get x prime equals 2a minus x. That tells me something interesting. It says if I know a, the value of that line, and I know x, the x coordinate of the original point, I've got a formula that gives me the x coordinate of the new point. That's really something, and that's what I'm going to call Anna's formula. X prime equals 2a minus x. Let's see if it worked on the problem we did originally. We had a point at 5, 2, and we had to see what its image was going to be. And we had a line at x equals 3. According to this formula, I can get the new x coordinate. I don't care about the y coordinate, it's going to stay the same. I can get a new x coordinate by multiplying 2 times a, 2 times the value of the reflection line, 2 times a, which is 3, and subtract x, the value of the x coordinate of the point. 2 times 3 is 6, 6 minus 5 equals 1. So that tells me this new point is at 1, 2, which is exactly what we found a little while ago. So this formula actually is something. Anna's formula gives us a way to compute reflecting across horizontal lines. In fact, there is a very similar argument that will give you a formula when you're reflecting across a horizontal line like that. Say it's at a point y equals b. The new y coordinate when you flip over that line is 2b minus the original y coordinate. So it turns out Anna's formula wasn't just one, it's two. One formula for flipping across vertical lines, like my example, and another very similar one for flipping across horizontal lines. You don't need to know this, I just found it interesting that Anna knew there was a formula, and it turned out to be a pretty simple. That's all I've got. I will see you in class. Thanks, guys.